Well, welcome to the second part of question 1 from the end of chapter 12, Fundamentals of Particle Technology. And in the second part, I'm going to cover part B, just this part of the question here, and part C as well. In the first video, I covered the assumption that all the particles were the same size when mixing a active ingredient which constitutes 10%, it's this 10% active ingredient in a pill, and the specification allows for a 10% variation around that active ingredient. So part A was covered in the first video. I'm now going to focus in on part B, where we have some data on the active ingredient particle size that's being used inside the pill. The other material, inert material, is 100 micrograms, and the active ingredient is 300 micrograms. So that's the data we're going to use. Right. Well, to make sense out of this, we need to use an equation for mass distributions, because we're being told the masses of these particles, and we're going to use the Poole equation. So that's Poole, Taylor and Wall, which says that the variance between samples or products is going to be equal to the product of the two components, P and Q, divided by the scale of scrutiny, the mass of the sample that's taken, or the mass of the product, because remember they should be the same. A sample taken from a mixture of powder should be equal to the same mass as the final product, which is a pill in this case, so that M is the mass of the pill. And then we have the average weight of particle P times by Q, the fractional component of the other material, against the average weight of the other material particle times by P. Okay, and in part B we're told that WP is equal to 300 micrograms, WQ is equal to 100 micrograms. P and Q we also know, because in this case we're going to use the weight fractions. The material is 10% by weight, active ingredient, and therefore the other material present is going to be 90%. So these are all values that we can put into Poole's equation. There are two things that we don't know in Poole's equation. Thing number one is the mass of the sample, or which we know will be the mass of the pill, but we don't know that either. And we don't know the variation between samples, the variance between samples. So these are two things that we don't know. But let's just develop our equation as we currently know it, and then we can talk about what we're going to use to help us solve the problem. So if we put some numbers in to the Poole equation, we have our variance again. This is the variance between the samples taken from the powder mixer. We know that we've got 0.1 times 0.9. We're going to leave M as mass. We know the weight of the particle is 300 micrograms, but I'll just call that 3 because I'm going to take some powers outside the bracket. So that's 3 times by 0.9 plus 1 times by 0.1. Okay, and then that's going to be 10 to the minus 4, because it was 300 micrograms and 100 micrograms, and 100 micrograms equals 10 to the minus, well, 100 times 10 to the minus 6 grams. So therefore that's 10 to the 4, 10 to the minus 4 grams. So that's where my 10 to the minus 4 comes from. We can simplify this equation significantly because sigma r squared is therefore equal to 0.09 over m. Then we've got 2.7, 3 nines are 27, plus 0.1, 10 to the minus 4. So finally we can come up with sigma r squared equals 9 times 2.8 times 10 to the minus 6 all over m. Right, and these are the two things that we don't know. We don't know the sigma r squared value and we don't know the m value. Well, sigma r squared is something that we can use an alternative means to determine. So we'll rearrange this equation for m. So we're going to be working out the mass of the pill depending on what we choose our confidence limits to be. So that's 9 times by 2.8 times by 10 to the minus 6 over sigma r squared, the variance between the samples drawn, or the variance between the pills, the final product. So now we need to talk about the values to use for sigma r, because clearly we're going to use this equation that I've just left at the top there to determine we're going to use the sigma r from an alternative supply, and the alternative supply is from the normal distribution, because we know that the active ingredient, this is what we said P will be, capital P will be, it's the weight proportion active ingredient inside the pill. We know that's 10% or 0.1. We know that there's some distance here, which I'll call delta x, between the mean value and something at the limit. Let me just illustrate this a bit better. If we're creating pills and we're analysing pills, we're hoping that the pill will have 10% active ingredient. So these are samples drawn from the mixture or pills drawn from the product, and we're analysing them and we're obtaining what we want, which is 10% active ingredient. But some of these pills will have less than 10% active ingredient, some of these pills will have more than 10% active ingredient. And that's not a problem, because we know we've got a certain specification where we're allowed a variation of, in fact, 10% on 0.1. So we know we can come all the way up to 0.11 and all the way down to 0.09 and still be within the specification. So we know that what I've called delta x there is equal to delta x. We know that is equal to 0.01. We can be that value above and below the mean value and still be within specification. Okay, now we use the normal distribution, because if this is 2 sigma, well, that's silly. Let's start with 3 sigma. If this was 3 sigma, and I'll have to call it sigma r to be consistent with what we've been talking about previously. So if that's 3 sigma, or 3 sigma r, then we know that that will be 99.8% of the distribution is plus or minus 3 sigma. In other words, one pill will be above and one pill will be below our limits out of 1,000, because 99.8 multiply that by 10 is 998. So we've got one particle, one pill rather, that will be down here, and one pill that will be up here beyond our limits, which we don't want. Well, if that's 1 in 1,000, and in the next part of the question we're asked to consider the out of spec values for 1 in a million, then that's going to be 2,000 particles. So in total there's going to be 2,000 particles out of spec. So 1,000 particles below the bottom limit, 1,000 particles above the top limit. So that's not good enough. So then we move to 4 sigma. Well, that's 100,000. So we've still got 3 particles at 100,000. That'll be 30 particles below the bottom limit, 30 particles above the top limit. Again, not good enough. Even actually when we get to 10 million, because this is 10 million, we've got 3 particles below, or 3 pills rather, as we're talking about them now, 3 pills below the bottom limit and 3 pills above the top limit. So arguably 5 sigma is just enough. We'd better really go for 6 sigma, because we know that we're now into 1,000 million. So there's one particle in 1,000 million that will be, or one pill rather, below 1,000 million down here. One particle, or one pill rather, above 1,000 million up here. So if we're going to consider a range, let's consider the range of 3 sigma to 6 sigma to illustrate what's going on, because that's what we're going to use for sigma r. Although technically speaking we're saying that that delta x, which I said was equal to 0.01, we're equating that with 3 sigma, okay, which is the standard deviation. So therefore I'll just write the equation that we're going to be using again just here, because it's going to disappear off in a moment. So we've got 9 times 2.8 times 10 to the minus 6 over sigma r squared. Then we can clear a bit of space. For the calculations. So to come back to the 3 sigma, to come back to this, just here, then sigma r squared is going to be equal to 0.01 over 3 all squared. So here we have a mass of particles equal to 9 times 2.8 times 10 to the minus 6 all over 0.01 divided by 3 all squared, and that will give us a mass in grams. And in fact that gives us a mass excuse me, a mass of 2.27 grams. So that is the mass of the pill. If we do the same calculation with 6 sigma, so let's put that underneath. If we do the same calculation with 6 sigma, so that will be 0.01. It's the same variation around the mean, only now we're at 6 sigma, where we know that we're talking 1,000 million pills. Then that gives us a value of 9.07 grams as the mass of the pill. Okay, so this 2.27 grams will give us a pill where we know 2000 are going to be out of spec. Not good enough. Here we know that we have very much less than 1 out of spec. Good enough. Arguably 5 sigma could also be good enough. But let's answer the question, because the question was how many particles does this represent? So we've got a final bit to do. Well, for the final bit, we know that P was equal to 0.1, Q was equal to 0.9, and now we know what the mass of the pill is. So if we take what we know isn't going to work very well, but if we take sigma equals 3, then that is a 2.27 pill mass times by 0.1. So that will be the mass of the active ingredient present, and we know that the active ingredient was 3 times 10 to the minus 4 grams, 300 micrograms. Then that gives us the number of particles, which is 757. So we've got 757 active ingredient particles. We can then do the calculation for the rest of the material, which is 0.9. Here it was 100 microgram for each particle making up the non-active ingredient component, and that gives us 20,430. In other words, a total of round about 21,000 particles present in our pill, which is a mass of 2.27 grams. It's out of spec though, so we really do need to work out the other extreme where we have sigma equal to 6, and where we have sigma equal to 6, that then becomes a 9.07 gram pill, which is times by 0.1 for the active ingredient mass fraction present, again divided by 3 times 10 to the minus 4. That gives us 1008 particles, and for the rest of the material it's 9.07 times 0.9 divided by 1 times 10 to the minus 4, because these are the masses of the particles, and that is 81,630. So this is 82,600, say 82,600 particles at 6 sigma, or 21,000 particles at 3 sigma. So this would give us, I mean, clearly the particles are really need to be small, and the pill sizes, well, this was a 2.27 gram pill, which is big. You know, the pill sizes are half a gram up to a couple of grams. That is a relatively big big pill. This one here is massive, let's call it 9.1 grams. That is a very big pill, but it's kind of inevitable that given such a big pill, you're going to have acceptable variation of the active ingredient if it's correctly mixed, if you're at the random mixing. So what should we really do? I think given these two extremes, probably we should operate at 5 sigma. These are the two extremes though, so we would expect a pill size somewhere towards the upper range here, heading towards the 9 gram pill size, and at that 9 gram pill size we would expect out of 1 million pills less than 1 out of spec per million. So that's looking at how to ensure a safe dose from our pill, because don't forget that most active ingredients are poisons. Hence, if we do actually exceed our maximum value, then we could be putting in a sufficiently high dose for an overdose from just one pill. So down here it's bad news, because we won't be providing sufficient active ingredient to do the job that's required. But at this end, at the top end, then that's really bad news, because we could be overdosing. Hence it's actually very important to ensure that we are within the appropriate range, and that might require us to have the physical parameters such that we can get this good mixing, which invariably comes from smaller particles. We were constrained by the actual size of the particles and masses of the particles used, which gave us this 9 gram pill. The most realistic thing to do would be actually to not have 300 microgram active ingredient, but to look at reducing that to something like 30 microgram active ingredient, and then we could actually bring that down to a suitable variation and a much smaller pill, so long as the massive active ingredient was still big enough to do the job. If not, we might have to take 2 pills rather than 1 pill. Okay, so these are examples of how we can use the solid-solid mixing to give us an idea on the formulation of the pills.